So there are some vector spaces that are not finite dimensional. Let's see an example of such a thing. Now, imagine all polynomials. So if I'll call this P infinity. Okay, we had P1, P2, P3, P4, where we were capping the degree. If we just don't cap the degree, okay, you still get a vector space. You can check that all the axioms are satisfied. So we'll say all polynomials with real coefficients, with real coefficients, or I should say the set of all polynomials. And let's look at some independent sets. You know, I could have B1, which is just, let's go with just T. You have B2, which is T squared. B3, which is, you guessed it, T squared, T cubed. And you can have B4, B4, B5, B4, 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 B5, B6, B7. Now, what is the point? The point is, these are all independent sets. So I have in P infinity, you have an independent set of any size you want. Okay, so it's not possible to find a finite basis. Okay, so you have an infinite dimensional vector space. Okay, we don't talk really at all about these in NYC, but I want to at least mention the possibility. Let's move on to a more pedestrian example. So we're going to find the dimension of H, which is a subspace of R2. So two-dimensional vectors that pass this test. Let's find the dimension of this thing. So what am I going to do here? Well, I'm going to look at, let's say I have a vector in H. What can I say about that? Well, I'm going to put an argument here that I'm very, very familiar with, but hopefully you will become familiar with. I'm going to start talking about what's called an arbitrary element in H, and I will obtain some information about the dimension of H. So what does this tell me? Well, I know that y is equal to 2x. So if I have something in H, that means y is equal to 2x. Let's give this vector the name x here. So I've added this here, call this vector here the vector x. So the vector x is going to be of the form, we'll have x, well that's going to be xy, but now y, I can replace that with 2x, can't I? Which will tell me that the vector x is something times this vector here. So what's the point of all this? Good question. So hopefully you agree that this argument goes both ways. Okay, this implies this, implies this, implies this, and backwards. But what I've shown is that if I have something in H, then it must be of this form. And if I have something of this form, then it must be in H. But what is this? This is a linear combination of this vector. So I can conclude from this argument that H is the span of the single vector 1, 2. Now remember, I'm trying to find the dimension. So what I'm going to do is I'm going to show you that this thing between my hands here, oops, I'm not covering up the span, this set here, without the span, is a basis. Okay, I've already showed you that the span of this guy here is equal to H. So I just need to remark that this guy here is independent. Why is that? Because it's a set of one non-zero vector. Okay, so there we have it. This set here, it spans H, it's independent. So it's a basis for H, and therefore dimension of H is 1. So I was able to find a basis for H and convince you that it is a basis. And then once I found my basis, I merely just say, well, there's only one vector in there, so my dimension is 1. Okay, in practice, you don't have to write all this. I'm doing so just for educational purposes, but in general, if you can proceed logically, find a basis, count the number of vectors in there, that's a dimension.